Okay. 1, 2, 3, 1, 2, 3. If you can hear us, if you can see us, please set the thumbs up in the YouTube chat so we know we can start.
Hello, everyone.
Yep. Hi,
Let's
hi
go.
Artem.
Hi, Alex.
Looks like we are good. Hi Prajaval, sorry, Laura. Hi Billy, Alessandro. Perfect. Many people, many dozens of people actually today with us. That's amazing. Cool.
It's good.
So looks like we are good. So with that, I want to start immediately because we have so
have a lot to
many
cover.
topics. Yeah, so many topics to cover. We want it to be very intensive. You came to learn, so let's go with that right now. That is the first workshop in Bootcamp application development series, which will consist of 3 workshops. First one is today. I hope you watch it live. If you watch it recorded, no big deal. Then because you still can get everything from this bootcamp. So more links coming soon, so you can stay in touch with us. First workshop, we want to focus on NoSQL databases, or to be more particular on one specific NoSQL database, call it Apache Cassandra. It's one of the most powerful and scalable databases in the world, used by hugest companies. We will discuss it soon. So that one really helps you to build high growth, high scale global applications available for customers from all around the world. Second workshop will be about data modeling. Today with me, and then the next week, you see Artem Chibatko, PhD, who developed data modeling methodology for NoSQL databases. So how do you build data model for applications this way? So your applications will be efficient, will stay efficient under any workloads, even working with hundreds, millions of customers. And then at the third workshop, we put it all together with the database, with a proper data model, with applications, and make it a real life running application, deployed and see it in progress. And you can pick language of your choice. So I believe most of you familiar with Python, Java, or JavaScript, and you can pick a language of your choice of this list. So let's go. I'm developer advocate lead at DataStax, Alex Voloshev. My job is to help developers not to fail with advanced distributed technologies like Apache Cassandra. And you will meet me multiple times during this bootcamp. Today with me, Artem Chibatko. Artem, could you please introduce yourself?
Yes, sure. Hi, everyone. Glad to be here. So I have 10 years experience of working with Cassandra, and I like Alex mentioned already, I authored the Cassandra data modeling methodology. We're gonna talk about it next week. This week, I'm helping with the hands-on and a couple of sessions related to CAP Theorem and some other stuff.
Cool. So, but this session is not about us, so let's move on.
Yes.
A little bit of explanation. We believe in hands-on practical education. We don't believe in just the boring theory. That means what you will need to push some buttons. It's all free and available for everyone, as all the software we are using will be running in a cloud. So you can do it basically with whatever laptop or PC you have. Everything, all the materials for the bootcamp is available on GitHub. It's all open source. You can use it in any moment, send it to your friend, whatever. Then to develop it and to run it, to make it operational, we will use Gitbot. Gitbot is a great platform, so you can develop code right in your browser and you don't have to install IDE, you don't have to run it locally. So it's like, I really love it and it helps developers a lot. And then finally, to avoid deploying Cassandra clusters and running everything on your own machine, which, well, software we are going to run is quite demanding in the resources points of view. We will be using AstraDB. AstraDB is Apache Cassandra in the cloud. It has very generous free tier. So again, it's free. You don't pay anything for that. And we will use multiple features of Apache Cassandra. If you are already familiar with this database, you can deploy it locally and do all the same exercises. But to simplify maintenance and our help to you during the workshop, we will be using cloud deployment. This workshop, is developers focused, not operations focused. If you complete for each workshop of this series you complete, you can get a special badge to brag on LinkedIn or Facebook or whatever social network you use. If you would like to get some acknowledgements, some achievements, then that is totally possible. To do that, you will need to do two things. First, watch these workshop live or recorded, this and all the follow-up workshops. And second, complete the hands-on part. You can do it with Artyom during this workshop or after that on your own free time later. It's also supported by us. And submit this as a homework, more details coming in the end of the workshop. And with that, I want to ask a few questions about you. We will use Menti, and Menti is a platform for us to ask questions to you and you can answer live. To join our quiz, please scan the QR code you see on the screen, or just go to menti.com and enter the code again you see on the screen. Easiest way and the most recommended way to do it is just to use your mobile phone. It's like the most convenient way to use the Menti. Good. I see people are joining, so let's start. I don't want to wait for too long. First question, I want to know how experienced you are. So what's your experience with relational databases? Okay, so we see people of different experience. Very well. If you didn't join yet, you can see instructions on top of the screen. Go to menti.com and use the code 62918600. We will ask questions during the workshop, so you better please join. Okay, I see with us some software developers, mostly probably, and I guess some students. If you have no experience with relational databases, this one might be a little bit rough ride because, well, NoSQL databases experience often based on SQL databases experience, right? But still, keep learning, keep doing. Even if you are now just zero, by the end of this series, you will have running application and you will get better understanding of how database and NoSQL databases work. Don't hesitate to ask questions on the YouTube chat or on Discord. There is Cedric Lundven to answer questions, and we will do our best to answer those questions as well. Now, next question. Do you already have experience with any NoSQL databases? Okay, so I see some people get some experience. That is good. If you have no experience, then congratulations, because you are right in the right place to learn something. NoSQL world is great and very interesting, many powerful and interesting technologies. And today we will introduce you one of the best of them. For the Discord link, I will send you a link, dts6.io/discord, https. That is a link to our Discord server and homework. It's explained at the GitHub repository link posted by Nightbot just a couple of messages above. GitHub DataStax Devs Workshop. Yep, thank you, Cedric. Good. So, very well. Welcome. You are on the right place to be right now. Then finally, where are you now? Like, it's very curious from how many countries we have people at the same workshop, but how global is our world? Isn't that amazing? Okay, looks like someone is on a ship. Have a good travel. Some people from Europe. I see UK. I see Africa. Amazing. I see United States, of course, pretty much expected. A lot people from India, Africa again. Cool. Any Australians? Australians must be sleeping right now. Okay, it's deep night. Oh, not Oakland, California, not too far from DataStax headquarters. Welcome. Cool. So, very well. And then final question, database you use the most, or maybe if you are a student, the only database you know so far, also will work to me. Hey, Aaron Plotz is in the chat. He is one of the best Cassandra experts, and I'm adding him as a moderator, by the way, beware. Good. Oh, so MySQL, Oracle, Mongo, pretty much expected. Well. Good. Postgres, again. Oh, there are some people using Cassandra already. Nice. I see DynamoDB. Well, so there is quite plenty of different databases. MySQL stays #1 so far, with some value, significant part of Mongo, and that is great. The most funniest part about NoSQL is what it's actually pretty bad definition, because it tries to group very different databases. MongoDB is a great database. I was using Mongo for years and I like it. And Cassandra is a great database. I love it and I use it also for many years. But those are totally different. We shouldn't group together, I don't know, submarines and spaceships. Those are different for different purposes. Today, those, if you use Mongo already, you will be introduced to your second NoSQL database, and that is great. Oh, I see people working with Teradata. Interesting. Good. So with that, beginning ends, and we will proceed to the next part. Quick introduction. How to use or how it works internally. I'm focusing on the question how it works internally, because you know what? I want you to be software engineers, not just people pushing red button if red light is blinking, okay? I need you to get some internal understanding. That's what makes us engineers. So today we speak a lot about how it works internally. And of course, we also work with how to use that. For sure, you need to know how to use that. But that will be mostly for the third workshop. Today, I want to get to the internals.
I'm just curious if in the chat people can answer whether they came to learn how to use it or how it works internally. It's 1 or 2.
You want me to switch to a previous slide?
Sure.
Okay, sure.
It would be nice feedback from attendees if they can. So they like both, how it works internally.
Yeah, actually both are important, but I see now many students rushing to use without willingness to get understanding of the under the hood parts. But it's very important to understand how it works internally. You know how to use, like we can train a monkey in the advanced question how to use, but how it works internally, that is something what makes engineer. Yes, so thank you so much for your answer. Yes, we need to take care of both. That is a good question. That's a good answer, right?
Yeah, thank you.
Okay. So let's move on. We now going to speak about why Cassandra, but that's not why you should use Cassandra. No marketing, no selling pitches. No. I want to answer a question first, why Cassandra was developed or invented, if you prefer. My point here is it's very important to understand the reasons of the technologies happen to be, because to build successful projects, we all, even they are not architects, just developers, junior, even maybe developers, we all need to think architecturally, think as an architect. And to get that, we need to understand the reasons and internals and whys of how this or that technology works. So here I'm going to answer a question, why Cassandra was invented or developed. And to answer this question, we are going to get my time machine, my DeLorean, and jump back to year 2008. Not so long time ago, just 14 years ago. 15, technically already, yes, 15, good. So the story started in the year 2008. Then Facebook reached their first 100 million users. And that is a very big number. Now there are plenty of companies with this count of customers, maybe even more people using that. But I believe Facebook was the very first one to reach this number. And that wasn't just a very, very big number, but more problems actually came to a place to solve. And I would first mention four of them. Users all around the world. Before, most of the businesses were all completely local or regional, or at least they were running as branches with not a lot of cooperation in between. By these years already, they were truly global companies, for example, Facebook. Second thing, and that is a pretty big thing, fast internet connection. Now in year 2023, people start to think like, okay, everyone has, we take it as given. Okay, fast internet connection, everyone has it. But that time it was a game changer. Beforehand, your database wasn't the bottleneck. Doesn't matter how fast your database, if a last mile internet connection from internet service provider to your customer will be slow anyway. You don't need fast database. It's okay. He will wait anyway. And now with fast internet connections, database started to be bottleneck. So it changed a lot. Now then a lot of data, more and more data, the volume what never was in action beforehand. And finally, with all of these, also new availability requirements came. If you ever heard about SLA, service level agreement, service level agreement means of how many or how fast your data, how fast your application should be, or what should be uptime desired for your application, when it must be available. And those SLAs for the performance, for like how quick response should be, they also started to get more and more strict. And scaling applications is a known problem, and that is a solvable problem. But by that time, real problem was scaling of a database. So there were no database like that. We were looking for a better database, and there were no way to get something like that. That what led to a creation of a new database we are going to use today. But before developing a new product, as we have to think as architects, even when we aren't, we still need to think architecturally. We need to define requirements, because without requirements, you are not going to build any successful projects. First, you define requirements, and then based on these requirements, you make architectural decisions. So let's first talk about what requirements do we put on our database management system. First, we speak about globally distributed system with customers all around the world. Single region deployment is no go for us. I mean, however fast, even if your database magically fast, but it's deployed in Australia and you are located near Frankfurt, you are going to wait for quite some time. You know, we cannot beat speed of light yet, maybe in the future. So we need to keep our database and our applications close to our customers, even if they are in the Brazil or maybe, I don't know, Japan or any region, doesn't matter. Our database needs to be close. Second, we are going to speak of volume and velocity. We are going to handle data of any size, and by any size, I mean petabytes of data, and also millions of queries per second. So we are developing a highly intensive application what's in use by hundreds, millions of customers. When we need it to be very fast, we have very strict requirements on response time. Basically, response must be nearly immediate. And then finally, we have very strict service level agreement on high availability. That means what our database must be available most of the time. If you are familiar with NINE's so-called definition of how much time your database or application must stay online, we usually speak about 4 nines, so 99.99%. It's called 4 nines. maybe 5 nines, 99.999% of the time, and so on. So requirements are going to be very strict, maybe 6 nines, maybe even more. It's actually like few seconds per year we can afford of a downtime. Then based on these requirements, we start to speak about architectural decisions we are making on that. So we speak about geographical replication and we need our data to be present everywhere. That means we will need to have multiple data centers in different regions. One data center maybe in the United States, maybe even two on different coasts. Data center in the South America, data center in Europe, data center, a couple of data centers in Asia, and so on and so forth. And moreover, if you are familiar with relational databases, you know they can support multi-DC deployments, but that is very typical for them to have active-passive. So you have one single active data center where you can read and write data, and multiple, one or more passive data centers where you can read data but cannot write it. In our case, we need to write data as fast as we read it too. So that means again, what we will need active data centers all around the world. That is not easy. People like that's not easy at all. Then for volume, we are going to have a lot of data and we are going to have millions of queries per second. What that will be our architectural decision based on that? We have no other choice to split our data into chunks. The story is working with relational databases. You have your data all stored on a single server. There can be leader-follower architecture with multiple servers, but still each one of them stores all the data you have. And you know what? That's great. That's very convenient, really, but that doesn't work with big data. Then you have petabytes of data of hundreds millions of customers. There is no server on the earth what could handle such volume and still be capable of responding very quickly. So we will have to split our data into multiple chunks, or we will call that partitions, and keep different partitions or different servers. That helps us to spread the workload, spread the queries over multiple servers, so we can handle more. Then, for service level agreement for time, we will need to use two things. First, to keep our database quick for response, we will need to use denormalization. Denormalization will be more discussed on the second workshop. So today it will be just like a very brief introduction. And as we partition our data, and we may have a lot of partitions over 1,000 servers, we need to route our queries to exact the servers storing our data. We discuss it very soon today during this workshop. And then finally, for service level agreement on high availability requirements, we are going to use two more technologies for replication and decentralization. What replication means? Replication means what? As long as you have your data, single piece on your data, just once on a single server, as soon as this server is down, this piece of data cannot be accessed anymore, and you have downtime. Replication means what we copy this piece of data on multiple servers, and if one of them is not, if one of them is down, we still can fetch this information from another servers. That is a replication. Obviously, replication means to a higher disk space consumption, but let's say big companies can afford that. Okay. Then decentralization is our idea. We don't want to follow a leader-follower architecture when you write to your leader or master server and read from replicas, follower replicas. We don't want it. That's a traditional database architecture, but that's fragile. As soon as leader is down, you cannot write, your application is not operational. No go. So replication and decentralization. So we discussed the requirements, we discussed the situation, many customers around the world, fast internet, a lot of data. We defined our requirements and we discussed our architectural decisions. And that leads us to a problem. In the world of the databases, in the law, in any field, basically, there is no silver bullet, one size fits all. Maybe no. We need more sport cars or trucks? We need both, okay, for different purposes. When very many thousands years before, hundreds thousands years before, each person, each human being was a hunter, gatherer, I don't know, farmer, whatever, warrior if required, all the things together. But over time, we as humanity, we developed specializations. Why? Because specializations are more efficient. Basically, exactly the same is happening with databases on the database field. From generalization, from multi-purpose, general purpose databases, we go more and more into specialized solutions. Because the problem is, if you want to have it all those multiple active DCs, partitioned data, denormalize it, replicate it, decentralize it, get back here. There is no database like that, or there were no database like that at all. And in 2008, there were plenty of great databases like Postgres, for example. Postgres is great, but it's more multi-purpose, and we need something more specialized.
Well, Alex, to
Yeah.
be fair, Big Table existed at that time, but
Yeah, okay.
maybe it was not available to Facebook.
Yeah, you see the
Because,
story
yes.
with Big Table. There are currently some solutions, database solutions, what are based on the same white paper and share the same concepts. For example, we can mention Google Big Table or Amazon DynamoDB. They
Yes.
are good databases. So I don't want to say anything bad about those. They have one limitation. They both share the same limitation. We really need to understand they are proprietary vendor lock-in database. So if, for example, you run your application on Google and you stick to Google Big Table, that is a great one. It will work well. But if for any reason you are not happy with Google and you want to migrate to Amazon, or you want to migrate to your own cloud, to your own data center, you will have to rework half of your application basically. That is a very important story, part of the story to me. So yes, Big Table was present. It's, I believe, like from 2005 maybe was available, right? I don't remember exactly. But it's a proprietary database. Well, I don't know about you guys, but I'm a big fan of open source things. And I see there is a question about the slides. Slides are available, and they must present on the GitHub repository. And James Wong asks, will the stream available on YouTube channel later? Answer is yes, the same link. Oh, thank you, Cedric. So, my point on this way from generalization to specialization, there are two sides on this field. OLTP kind of workloads and OLAP kind of workloads. What is that about? So see, OLTP stands for Online Transaction Processing. It's usually customer-facing databases with a lot of operations per second and very strict service level agreements. And that is very specialization, like they have to be all the time up, serving a lot of queries very, very, very quickly. That is very specialization. Another side of this field, opposite side of this field, is OLAP type of workloads. OLAP stands for Online Analytical Processing, and that is a very different kind of workload. That's usually about data exploration. That is usually about like analysis of your data. A lot of data, very often historical, so-called cold data. And very often it includes some kind of a very complex queries to run, like with dozens of joins. Let's find all the customers who has bought car tires last year, but did not bought any kind of, I don't know, laptops the previous year, and then they bought car tires, it was rainy, and if they are younger than 30 years old but older than 15 years old, and so on and so forth, like with dozens of joins with very different aspects.
The classic example in that field is the question that was asked for like grocery stores, retailers, find fathers who bought diapers and beer at the same time on the same trip. So essentially, would help would place beer and diapers in the same or same section or nearby, so that customers can find those items.
Yep. And the story of this is you cannot be simultaneously on the both sides with a single project. So most of the relational databases, they are more multi-purpose. They're trying to stay in between. And that brings us to a problem, jack of all trades, master of none. So they can try to get into OLTP processing, but they're not perfect in it. They're trying to get to a lab side of the things, but again, there are much better solutions what are specialized for analytics. And that's why that was the reason why relational databases were dominating databases market for dozens of years. They are versatile, they can be a little bit on each side of the field. But if you need to have more, if you really need to have petabytes over multiple regions answering 15 single-digit milliseconds, you need to sacrifice something. What is the sacrification? Idea is very simple. The more you get to the right side of the field, better you are on OLAP, but worse you are in OLTP. And opposite, the more you get to the left side of a thing, better you are on fast dispatching millions of queries, but not as good in search capabilities, in analytics capabilities, for example. It all comes with a price, right? So, what world desperately needed there was an open source, distributed, decentralized OLTP database, customer-facing database, with the ability to have it presence basically everywhere in all the regions, answer all the questions very quickly, and we are ready to pay for it, sacrificing some of the ALAP capabilities of the databases. What is it now? So, at what all the story about Cassandra? What is Cassandra today? Now Cassandra is used basically by all or almost all of the huge transnational corporations. Biggest Cassandra users include Apple, Huawei, Netflix, Instagram, IBM, and many others. Basically, you all use Cassandra, even if you don't know it. All the global companies are using Cassandra, or at least it's a proprietary proprietary implemented solutions of the same style. Cassandra scale, what Apple uses is at ApacheCon year 2022, last year, so Apple reported what they have over 300,000 database servers for Apache Cassandra. They store hundreds petabytes of data, and they dispatch millions of queries per second with Cassandra. Then my favorite example of Cassandra usage is actually Netflix. Problem with Apple is what Apple doesn't tell us a lot about how they use that. It's secret, you know. But Netflix is much more friendly and much more open to us. So Netflix shares a lot of their details on how they use Cassandra regularly. And Cassandra is the primary database for Netflix. So Netflix, of course, uses multiple different databases, but Cassandra is definitely primary. The single most active cluster, and they have multiple clusters, handles 30 millions operations per second, reads and writes. And overall, they have hundreds, thousands of clusters, hundreds or thousands of clusters by now, I believe, with, again, hundreds petabytes of data. If you're more interested in how Netflix uses Apache Cassandra, you can follow this link, dts6.io/Cassandra at Netflix. It's the talk what was done by cloud database architect Vinay Kumar Chella at last Cassandra Day India. I recorded this one. So, question. Oops. First real question. Switch to Mentium and tell me, Cassandra is better fit for OLAP workloads, OLTP workloads, or both types of workloads? Let's see who paid attention. That is actually a little bit tricky question. I will explain when you will answer. Don't be afraid to make mistakes. You better answer using Mentium, so your vote will count. Yeah, there is a tricky question. Cassandra was designed to be much more on OLTP side of the things. That is for sure. But there are some kinds of OLAP workloads what also can be answered for Cassandra if it doesn't include a lot of joins, for example. Then you just want to see time series data of what is temperature change in particular region of a particular temperature sensor stored in Cassandra. Then you can see this data easily. Yes, that kind of works, but that is a very limited side, very small part of what's happening on OLAP side of the world. Cassandra was designed to be OLTP database. And there is no simple solution to answer both types of workloads because there are no silver bullets in the software development. In anyone comes to you and says like, hey, you should try this database. It's just the best. Don't try this person. He's going to sell you something. Idea is it's just not possible. What is better, submarine or airplane? That is a stupid question. People, that is a really stupid question. They both are good. It just depends. Do you have to dive in the sea or do you have to fly above the skies? Like, you are not going to fly very high in a submarine, right? But that doesn't make submarine bad. You just need to have some specialization, okay? Good. So, let's get back. So what are the features we speak about? What are the primary features we speak about Cassandra is built internally? First, it is partitioning. We split all the data we store into multiple different chunks. It is very important for us because those chunks can be stored on different servers. And if we need to store more data, we simply can add more nodes and put those chunks on those new nodes, and we will be good. Partitioning is very important. Don't get me wrong, partitioning creates also quite some problems. You will see it soon. But it helps with scaling, that's for sure. Of course, very important thing for us as OLTP database is very high read-write performance. Cassandra is very well optimized for both writes and reads, and it's definitely one of the fastest databases in the world. Even a single Cassandra node is very performant, but as the nodes work together, that always helps with read-write performance. If, for example, one node is slow, but your query still will be processed and dispatched sooner with another node which is not slow it down for whatever reason. Very cool thing. Scalability, but not just scalability. The idea is, first, Cassandra scales horizontally. Most of the databases you are familiar with, they scale vertically. That means what if your database cannot cope with the workloads you put on it, you buy a bigger server, migrate your data to a bigger server. Mostly probably it's a downtime operation, so your application will not be available during this time. Then you launch it again. And then what happens next? Then your new database again cannot cope with this workload. You have more and more customers. You get another server, migrate your data, and so on. Vertical scaling means getting bigger and bigger servers. You know what? At some point you realize there are no servers bigger than yours, and you still get more and more queries from more and more customers. Vertical scaling has limits and also getting prohibitively expensive very soon. Cassandra scales horizontally. It means what we don't upgrade our nodes, but just add more nodes, add more servers to a cluster. Let's call it horizontal scaling or scale out. For volume or velocity, if you need to process more queries or if you need to process bigger data volume, you just need to add more nodes. But my favorite thing is how exactly it scales. The story is for most of the databases, introducing new servers to a cluster had its overhead. It means what each next server will bring you less and less performance. And take a look. Netflix did a very interesting research some time ago, scaling their cluster from approximately 50 servers to approximately 300 servers, and meanwhile measuring workloads. And take a look at this nice straight line. The story is for most of the databases capable of scaling, this line would get somewhere here, much below. It wouldn't be straight because each next server adds some overhead and more until at the situation then every next server gives you nothing. And this line basically shows like how Cassandra scales linearly, and adding more nodes you get more and more volume and ability to process queries and still get that on time. Please notice this mark. You know, when you read contracts, I don't know, whatever, mortgage or loan contracts or job contracts, you really need to pay attention to a very small text on the bottom of your document and to marks like that. Those marks are very important. Here is the same trick. This scalability works, but it's not only Cassandra's job to do it. To reach this scalability, you need to very well understand how to do your data model right. And if you don't do your job, it will not work like that. So you still have to do your job. Lucky for you guys, the inventor, developer of data modeling methodology is with us today, and he will be with us next week. And next week workshop is all dedicated to data modeling and how do you do your data model right, so your application may work efficiently and your system will scale, even handling millions and millions and millions of customers from very different regions.
Alex, I would
Yeah.
add for this graph, so when we talk about scalability, we sometimes say, okay, will it scale from gigabytes to terabytes to petabytes? This is one notion, like ability to store large data sets. And on this graph, we're actually looking at different type of scalability. It's a throughput, high throughput. So essentially, we measuring how many operations per second can a cluster process. And of course, when we add those nodes, we can also store data, more and more data on those nodes, but also you can see it scales linearly in terms of this throughput. And the big question here is why do you care about this, right? Yeah. So if you expect to build an application that is high growth application, that is going to eventually grow and grow and add more and more users that generate more and more data, then you should care about this, because this is going to be the only way how you're going to scale. You don't want to non-linear scalability. You want to scale linearly in this case.
Yep. Good. Okay. Yes, James, of course. For reads, you see, very good point from James Wong. That is about client rights. The point is why we show rights here is scaling for reads is easy. Scaling for reads, you just, even in traditional architecture, primary server, a follower server, you just add more follower servers, you spread read workloads over multiple servers, and you will be good. Then scaling for write is a real problem, because in traditional architecture you cannot just have two master servers or two leader servers. That is a problem. Yep, and to Adriana, I see Cedric answered it already. In Cassandra terminology, node and server is basically the same. It's just synonyms. Node is a server with Cassandra running on it. So simple as that, yeah. Load balancing, we will explain soon. It comes, you will see it. Good. Next thing, highest availability. We discussed it already, what we want our application to be available all the time. First thing, we cannot have high availability without replication. We need to have the very same data, but copy it on multiple different servers. And that is a very important thing. So the data is placed on different servers, usually on different regions. Then decentralization. Decentralization means there is no idea of a master server. All servers are the same. It's decentralized peer-to-peer architecture. Artyom will soon say more about that. So no single point of failure. There is no outage of the leader server. Then network topology aware data placement. So there is a thing like if you do a backup of your laptop disk, you will not store this backup on the same disk on your laptop, right? It makes no sense. Then if your disk is damaged or I don't know, stolen, you don't have access to the backup files, right? If you make a backup, you put it to a different place, preferably different physical location. Cassandra is very smart from network topology point of view. So those different replicas must be first obviously on different servers, but preferably on different server racks, or if we speak cloud, on different availability zones. So outage of availability zone or outage of a single server rack doesn't lead to outage of all available replicas, obviously. And then finally, cloud the very smart client-side reconnection and retry mechanisms. So Cassandra drivers, mostly developed by DataStax, also very smart, and they know how to reconnect, how to find different nodes, and so on and so forth. I see there are some great questions in the chat. I hope we will have a chance to answer them soon. I want to get to that, but first I want to finish this part of the slides. Now, very important thing for me per person as someone also responsible for operations for some big applications, clusters and things. Operations and maintenance of a huge cluster can be very exhaustive. Apache Cassandra clusters are very smart and there are many of operations automated. So introducing a new node, moving data, recovering from inconsistency, recovering from outage, changing data placement because of some changes. Very many operations are automated. There are some level of self-healing introduced, and very often we can recover from a bad state completely automatically with no manual operations required. Not always, but very often. And that, like, I'm a lazy engineer. If I can avoid some work, I will avoid this work. And then database is doing my work for me. I'm totally happy. Good. And well, geographical distribution already discussed, so I don't want to stick on this slide for too long. Just one more thing, just one thing again, often misunderstood, data centers all are active. So you can write and read to and from any of the data centers, in this case, one in United States, one in Europe, and one in Asia. Now, thing mentioned before by Artyom, Cassandra is open source platform agnostic. So you can run it on your own data center, on Google Cloud, Microsoft Azure, or Amazon Web Services simultaneously. And all those data centers can build a single cluster. So you can survive outage of the whole cloud, even if the whole AWS gets down. Somehow you still will have 3 data centers here on this example running successfully. Same data, same data center. Good. Yeah, as mentioned, Cassandra is, well, many people know what DataStax is like commercial phase of Apache Cassandra, we could say. But actually, Cassandra does not belong to any commercial vendor. Cassandra belongs to and controlled by a non-profit open source Apache Software Foundation. which you might know by projects like Apache Kafka, Zookeeper, Maven, Hadoop, Spark, and many, many others, maybe Airflow. There are plenty of different products you may know. Last thing on this part before we will be answering questions. Yep. There is a price to pay. You remember it before we said what specialization is effective. Yes, but specialization means what you cannot be good in all the things. You spend some time becoming a doctor, I don't know, dentist, or whatever, cardiologist. That mostly probably means what you are not going to be a very good race driver, right? Because your time is dedicated for like biology, all the kind of things what relate to human body and so on. And you don't have time to become a race driver because it also requires a lot of time. And the same with race drivers, they're not going to be good doctors, most of them, right? So what are the limitations we are going to encounter very soon? First, Apache Cassandra supports no joins. There cannot be joins between multiple tables. So you will see that soon. Operating data, you need to know the partition case because data distribution partitioning is based on the key. We will show it soon in a moment. Don't focus on that right now. But there are some limitations on how could we execute the queries. Very limited search capability. So if you need to have a full text search, then mostly probably you will need some collaboration between Cassandra and, for example, Elasticsearch. And of course, running big clusters usually require a lot of qualified personnel. Developers, operators, and so on. We at DataStax work hard to make things simpler for the global software development community around the world. So first thing my answer to the requires qualified personnel. First of all, yep, you want to say something?
Yeah, Alex, how about ACID transactions? Does
Okay.
Cassandra support ACID transactions? Because this is usually pretty important for and pretty standard in relational database.
Yes, right. Well, it's a complicated question because current version does not. But it comes in Apache Cassandra version 5 to be expected release somewhere 2023, somewhere this year. Oh, this year already. Amazing. Yeah. So yeah, I have to add this thing to this slide, right? Consistency may be challenging in some situations.
So with all these limitations, why would I want to use Cassandra?
Because it's if you want to have all of these, most of all, Cassandra faces OLTP workloads, but for many scenarios, you may need to use a data platform like we have, for example, with Astra. DataStax Astra is a data platform based on Apache Cassandra, but extended with some new capabilities. Well, this workshop, we are focused on the open source side of things. But if you want to answer dozens, millions of queries per second, over the world, you need to pay something for that, right? I don't mean money, but yes. I mean capabilities here.
So scalability is unmatched. Relational database cannot scale.
Nope.
The way Cassandra scales. And the other thing is the availability, right? The relational database cannot do that, cannot provide high availability that we talked about.
Thank you so much for mentioning that. Like, I was many times in a situation when I talk with some developers at a conference and I say, like, Cassandra scales better than the database you are currently using. And like, what do you mean? Our database scales too. What do you use? Postgres. Okay, Postgres is a good database. Amazing database. It's like for many use cases, Postgres will be better than Cassandra. I mean, like, yes, sure. But what is that? What do you call scale? Like, what is your workload currently? Oh, we handle up to 30,000 operations per second. That's cute. That's cute. When I speak about scale, I mean millions operations per second, not thousands, not dozens thousands, not hundreds thousands. And there at this place, or multi-data center active. Postgres tried to have multi-active DC, but with traditional relational databases, it's nearly impossible. Yeah, so that is the benefit, let's say.
We have a good question whether
I'm sorry, I have to finish this slide first, and let's get to questions afterwards. So, required qualified personnel, there are two answers from me. First one, very important one. There were a question in the chat before, what about the certification? DataStax sponsors your education and certification as Apache Cassandra developer or administrator. So you can get your trainings, take your exam and become a certified Cassandra developer or administrator completely for free, sponsored by DataStax. And that's our first answer. Second answer is Astra. Astra, you will see today, Astra is a way for you to use Cassandra as a database as a service with no need for you to maintain and service and do all the things required by a database cluster. It will be done by DataStax. So it's really a very good solution for the cases you prefer to focus on your customer needs and don't spend your time maintaining a database. Very limited search capabilities. Very limited search capabilities also has an answer. Cassandra works perfectly, for example, working with Elasticsearch. For some cases, you may need Apache Spark. So for huge deployments with multiple requirements from both OLAP and OLTP, you may need to use multiple projects simultaneously. Recently, we introduced change data capture for Apache Cassandra and open source change data capture for Apache Cassandra, which helps to communicate Cassandra with multiple different technologies you may need to work together with. And so there were questions you wanted us to answer, right?
Yeah, there was an interesting question whether if we introduce multiple data centers, will performance slow down? Will it be slower? Will there be overhead? I'm rephrasing it.
Okay, you mean question by Mao Andy?
Yes.
In real world setting, do we have many cases to set up different DC in different continent, which incurs higher latency? No. So first answer is yes, there are many scenarios where you want to have your data centers in different regions. First of all, for disaster tolerance. Second of all, for to keep your Australian clients working with Australian instance of a database, so it will be quick.
So it's going to be faster response, essentially.
Yeah, but there is a point what incur higher latency, and that is wrong. The story is your application server in Australia will work with our Australian data center and will not wait for European to answer. It writes data to Australian data center, and when Australian data center will communicate this mutation to all the other data centers asynchronously. Well, it depends on your consistency level settings, so there may be different scenarios. But in short, working in the Australian data center, you don't want for European data center to answer, okay? Yep.
But for replication from one data center, data is replicated to another data center in real time. So that latency will increase, of course, because we're talking about larger distances. But like Alex said, your application will work with one data center, which is the closest to that application. So the latency decreases in that case.
Sorry. There is a good question by Tejas Kumar Patel. In relational databases, real application cluster give horizontal scalability. How it differ? The short answer is no. In relational databases, horizontal scalability is reachable only for read-only replicas, so-called slaves or follower servers. And for them, you can have horizontal scaling, but notice you have horizontal scaling only for reads. Because why? You cannot write to follower servers, they are read only. So, and to get horizontal scalability for writes in relational databases, it's technically just impossible because for most of them, you cannot have multiple master servers. Simple as that. Um, okay, Melroy Tellis. Sorry, yeah, you wanted to add something?
Yeah, it's a loaded question. I don't want to go deep into it, but we will talk about a little bit about scalability next in the next session.
Yeah.
Horizontal
Multiple.
partition.
Sorry.
Yeah, go ahead.
Melroy Tellis. Multiple data centers may also be a setup to comply with data localization requirements by governments. Yes, absolutely. It's one of the things where you can put your different data into different data centers, depending on the region. Yes, that's how it works. And which language will you use for the hands-on activity? For this workshop, we will stick to Cassandra query language, which you will soon discover, and this one looks very familiar to you because it's very similar to SQL, except some capabilities like joins. Mohan Palival asks about Cassandra DB data modeling comparing to relational data model. It comes next week. So see you next week with that.
Come next week, we will talk about it.
Load balancing is to be explained soon. Okay, others discuss set. Okay, then I asked your questions. Now it's time for you to answer my question. And that's going to be question number 9. Number 2, switch to Menti. Answer my question. How do we scale Cassandra cluster? Scale up by upgrading servers. Scale out by adding servers. Cassandra cluster does not need scaling. Meanwhile, the CGR asks how a data center data center cluster terminology. In short, cluster consists of multiple or one or multiple data centers. Data center consists of one or multiple nodes or servers. Node and server basically synonyms in this terminology. And Cassandra scales horizontally by scaling out. That is the way how you scale Cassandra cluster horizontally, not vertically, not by scaling up. Okay.
So it's one cluster, multiple data centers.
One or many. Yeah. Good. Well, then that brings me to the point I have to switch the screen to yours. Are you sharing?
I am, yes.
Perfect. So give me a moment. I think you are live. Please
Okay.
try to change the slide.
So we have 5 more sections, 5 more hours to go. Just kidding. So let's talk about some of the concepts that we briefly touched. So one of the important things that you want to remember about Cassandra is that all nodes, all servers are equal. So they appears there is no special server that is doing more than other servers. And that means, why is it important? That means that if we lose one server, we basically can easily replace it with another peer server. So there is no concept of master or leader, and this is probably one of the most important things to understand in the architecture, in the cluster architecture. So traditional architecture, many times we see distributed databases, they follow this a design pattern where they have leader and they have followers. So essentially they you can think about the leader is going to always get all the rights and will send those rights to all the follower servers, or you can say they are replica servers as well. So they will store the data, they will replicate the data. But however, so when you're doing right in this architecture, it always has to go through the leader, and that's a problem. This is single point of failure, and writes will not scale with this architecture. So there are multiple solutions that different databases to try to improve scalability for writes. They create multiple leaders. They have standby leaders. So if one fails, they come up, they bring another one quickly, and all of that. But it's still very hard to scale writes. So if you're worried about writes, you should look at the database that does not follow this architecture. However, for reads, if we're talking about reads, um, we uh, we can process reads using follower servers. So reads do not have to go through the leader. They can go directly to the followers. And therefore, because there are many followers, we can actually scale reads pretty well. Okay, so in those databases, scaling reads is easy, scaling writes is hard. And now the so-called peer-to-peer architecture, which is Cassandra architecture, and a few other databases use the same type of architecture. Here, each node, each server is essentially identical, and they talk to each other. They know which server stores which data, and if one server, so the data is also replicated. If one server fails, it's not a big deal because there are replicas, and they can answer the same, exactly the same read request, so they can retrieve the same data. So no single point of failure, and that means high availability, but also we can scale reads and writes very well in this architecture. Now for Cassandra specifically, we had a little bit of discussion earlier. Writes are very efficient. You cannot find a database that would do much faster than Cassandra. Those that do faster will be very simple key value stores, most likely. So because Cassandra simply writes data into commit log, and it write is done, and then it does additional. But reads can be more expensive in Cassandra, so because certain data structures need to be processed and data need to be retrieved, and there can be multiple of them. We are not going to touch that. That's mostly internals, but what you need to remember is that both reads and writes will scale great. Writes will always be super efficient. Reads may be less efficient, but still very efficient, real-time performance. So we're talking about single-digit millisecond performance. So also data is partitioned. Data is stored in tables, but those tables are partitioned. And since we already mentioned horizontal partitioning, indeed we are using horizontal partitioning there. They are partitioned based on partition key. So here is an example of a table sensors by network, and we have three columns here. We have rows, so columns network, sensor ID, and temperature. So this is how defined, pretty similar to SQL. If I didn't tell you that this is Cassandra query language, you would easily think that this is structured query language used in relational databases. So the difference is to do the partitioning, we need to assign one key, one of the columns to be a partition key. So in this case, we're assigning network as a partition key, and that means that any row that has the same value for the network will end up in the same group of rows called partition. So, and essentially those partitions, so everything with a network name California will end up, all those rows in the same partition, and Alabama, the same thing, Kansas, the same thing, and then there will be data distribution that each node will be responsible for certain partitions. So the data will ideally be identically distributed across nodes in the cluster. Okay. So we're talking about distributed table here. So this is how partition key defined in Cassandra query language, CQL. It's a network column. So you can see the same three columns: network, sensor, temperature, and network is here defined as part of primary key, but it has special dedication as a partition key. So one way to dedicate a column as a partition key is to add additional parentheses. or by default, the first column will be the partition key. So the partitioning of the table will happen based on the network column, and distribution will also have this on this partition key. So you may wonder, what is this sensor? It's part of the primary key. Why do we have it? It's actually called clustering key, because within a partition, you also want to be able to identify different rows. What makes those rows within a partition unique? And if you go back, so California is a partition key. So two rows will end up in the same partition. What makes them unique? The sensor ID makes them unique. So you can distinguish. If you want to retrieve whole partition, you specify partition key. If you want to retrieve one specific row, you need to specify partition key and clustering key. So it's like row ID inside of a partition. Okay, so based on the partition key, the values in the partition key column, there will be murmur-free hashing partitioner used that will convert those values, Alabama, California, into numbers. And those numbers will be large numbers. We're using small numbers just for the sake of simplicity for this example. And then, so all of them will be converted to numbers. And then Cassandra nodes will be assigned ranges of those numbers. Those numbers are called tokens. So each Cassandra node will have a range of tokens that it will be responsible for storing. And in reality, there will be multiple ranges assigned. So if we have four Cassandra nodes here, then the first one, and we have 100 tokens, of course, the value is much larger. But for the simplicity, we only have 100 tokens, and the first one store 1/4, so it's 1 to 25. The second one 26 to 50, and so on. So what's partitioning? Alex, I can hear a lot of noise on the background.
Oh, sorry.
So why partitioning, and how it's related to sharding? So because scaling doesn't have to be sharded. I think I may have T-shirt from 10 years ago that says that. But the sharding went actually a long way. It's no longer, it's not manual sharding. So the relationship of these two concepts is partitioning is more general notion of dividing a table or data set. In our case, it's a table into chunks, and we can divide it either vertically. So we decide, okay, this part of the table, some of the columns will go to a different table, and the other columns will go to another table. So we get two tables. That's vertical partition. We are not using it here. And horizontal partition is we divide table horizontally, so chunks of rows, groups of rows will go to different partitions, right? So that's what we're using here. And sharding is actually refers to that horizontal partitioning. So it's one special case of partitioning is horizontal, one special case of horizontal partitioning. Okay, and so here is an example with of scaling your cluster. So if you have these token ranges, if you have 4 nodes in your data center, or even just in the cluster, just think about it as a cluster with one data center. If we add another node, we basically need to redistribute the data, right? So we are going to scale out. Each node will be responsible for smaller token ranges. Okay, but there will be more nodes, and therefore the throughput increases, how much data they can store in those ranges increases, and all of that. And this operation is not necessarily super efficient or inexpensive. It's not an inexpensive operation because you have to move data between different nodes, right? So scaling in is when you no longer need that many nodes. Your throughput is lower. You don't need to store that much data, so you can decrease to 3 nodes, and then you basically have to repair those nodes to move data around. And repair, by saying repair, this is the utility that you run in Cassandra. It's not manual process. So this is how it can scale out, scale in. And some systems like AstraDB do it for you automatically. So you don't even know how many nodes you have in your cluster. They all basically, whenever throughput increases, we increase the number of nodes for you increases, and we will decrease it. And therefore, it's you saving on resources and all of that. So another important notion in Cassandra is replication, data replication. Alex, could you please mute yourself?
Oh, sorry.
So replication factor, the replication is done based on replication factor in the cluster, or it can be, if you have multiple data center, you can specify replication factor for each data center. So replication factor means the number of nodes that will store the same partition. So the same partition will be stored in multiple replicas. So if replication, so how replication factor is specified is, again, when you create the key space, and key space is basically represents your database. It stores, it will be a container for tables, for indexes, for user-defined types, for all the schema elements. So when you create the key space, you specify replication strategy. In this case, it's a network topology strategy. And replication defined, the replication factor defined for each data center, US West 1 and U East 2, we get 3 and 5. Okay, so in the first data center, we're going to have 3 replicas of the same data. And in the second data center, we'll have 5 replicas of the same data. So totally 8 replicas. So we can lose as many as 7 nodes, 7 replicas, and we still have the data. Of course, we never want to wait until that situation when we have the last one. We need to take an action.
So there is another complication, because with for losing 7 nodes and still get our data, it works, it's achievable, but it brings some implications. What Artyom will say soon at the 4th part of the workshop.
Yep. So with replication factor 1, we only store 1 copy of that partition. With replication factor 2, we store 2 copies. We have 2 replicas. Those are different nodes, and we store 2 copies on different, or 1 copy on each node. With replication factor of 3, we have 3 different copies, and so on, right? And what it looks like internally is basically, with replication factor of 2, this node is now responsible for 2 token ranges. It used to be, with replication factor of 1, it was responsible for 1. Now it's responsible for 2 token ranges. And this node is responsible for 2 token ranges as well. But it doesn't make them special nodes. They just assign different token ranges. That's it. They function identically and all of that. So with replication factor of C, when we combine in partitioning and replication, what happens? So we need to store this partition with 2 rows in our cluster. This forest partition key will be converted to a token. Let's say it's 59, and based on this 59 token, so the application can send this request to any node in the cluster, and that node becomes coordinator of the request. So we get 59 to this node, blue node, and this coordinator knows exactly which replicas are responsible for 59, for token 59, because it knows ranges of all the other nodes. Okay, so it will take the data and will send that data to all 3 replicas, because replication factor is 3. So it will send the data to all three replicas, and in the normal circumstances, all three nodes will get that data stored. Okay, and of course, to optimize it, right? To optimize it, in Cassandra, when you write in your application with data stack driver and data API, the interfaces are token aware interfaces. So essentially, your driver will also know which nodes are responsible for. Your driver also know which nodes are responsible for the data. So it will not just pick any coordinator. It will pick one of the replicas as a coordinator, so that it speeds up things. You have to do less work.
I want to say a word here. I don't like the word coordinator because it's actually misleading. I prefer to call it query coordinator, and whatever node has got your query is the query coordinator, because people often start to think about that like master node, which is wrong.
Yeah.
Every node is query coordinator node as soon as it processes your query, and each node may get your query depending on how driver is behaving. No, answer to Adriana, Cassandra driver is a Cassandra driver. Query coordinator is one of the nodes it's decided to contact. In most of the cases, query coordinator will contact one of the replicas for the partition you are trying to work with.
Yeah, even better term is request coordinator, right? So
Yeah.
it's not only query, it's both reads and writes. Indeed, coordinator has nothing to do with master or leader that we discuss in the architecture. It's just the temporary role that just to perform that request, just to forward that request to correct replicas. Yeah, and Cassandra driver, one of the questions, is it coordinator? No, Cassandra driver is just a library that allows you to connect to Cassandra cluster from your application written in Java, Python, JavaScript, and so on. So now we're gonna do our first hands-on with Cassandra, but we're not gonna use the local installation. We're going to use instead the cloud-based service that is built based on Cassandra. It's called AstraDB. So for our purposes, what we will use is going to be a free part of free plan. You may have to register, sign up for that plan, and you get a large amount of storage and large number of operations every month. So you don't need to worry. There will be no credit card asked or anything else. Why do we want to use this? Well, for hands-on, we're not worrying about operations. We want to start using the database without dealing with installing Cassandra on a node, installing a second node, connecting them.
I
Yes.
would say without Astra, this workshop would be like 4 or 5 hours duration, right? Not 2.
Indeed.
Okay,
Yes.
we will not fit into 2, but 2.5, let's say.
Yeah. So there are many good features about this cloud service called AstraDB, but I will just mention two that for me it make a lot of difference. Is one, no operations, so you don't need to install anything. You just click on the buttons and the cluster is running in the cloud for you. You just start interacting with it. In our case, we will use CQL shell to interact with that cluster. And the second one is the serverless feature. Remember when we talked about scaling in and scaling out? So all of this is done for you automatically. So it's auto scaling that is built in as a feature of this database. So you don't need to worry about adding nodes if you need to store more data or you need to process more concurrent requests, and you don't need to worry about scaling out. So in case, for example, you have during the day, the usage is higher, automatically you will get a larger cluster built for you. And you don't worry about it at all. You don't do anything about it. It's just automatic. And at the night, the usage is lower and the number of nodes decreases automatically for you. So you don't need to spend extra resources. So our first lab will be to use this magic database called AstraDB. We will create, and it's built on Cassandra. Again, we are not going to use any features that are not Cassandra features as well. So we will create tables, we will insert data, we will query data. Okay, so let me. So this is the URL that you can use to access the hands-on instructions. And the first one is it's going to be really easy. Okay. So this is the first one. Create your database. Okay. So this is the link you can follow to go to AstraDB website. Okay. And there you will, if you don't have account already, you can sign up, and you can sign up with your Google account. If you already have an account, you can sign in. What we will do there, we will simply create a database with name workshops, okay, and key space name sensor underscore data. We will use Google Cloud Provider to deploy our cluster in, and you will see what happens, whether it's difficult or not. So I'm clicking this, create AstraDB. Okay, and I get to this screen. So I'm going to sign in this case, with Google account. Okay, and I get to this screen. Okay, I will wait a little bit. How many people are already signed into Astra website? Can you confirm? Can you confirm in the chat, or do you need time to sign up first?
Okay, so people like it. I mean, like sign up using Google account or GitHub account is.
There are just a few extra questions there.
Yeah.
Okay, we get in the sign in.
Yeah,
That's
good.
So the next step, you can go to databases, and it's, if you haven't used this database before, there is nothing here. So it says there, create database. In my case, I don't have any databases. So I will create database. Okay, and we need to specify the name of the database and key space name. So workshops is the one, the name of the database, and key space name is sensor data. Okay, pretty simple. And you can see this is a free plan. There are certain restrictions on where I can deploy my cluster, and essentially I can deploy it in the Google Cloud. Okay, and I will use North America. I don't think any other, oh, there are some other regions. If you're in Europe, you can use Belgium. And if you're in Asia, you can use Mumbai, India. In my case, I'm in North America, so I will use the South Carolina, US East 1 as my region in Google Cloud to deploy the database. So these are 3 steps, right? Or 2 steps technically, right? The database name, key space name, and the provider. Then create database. And at this point, it may take a couple of minutes. What happens behind the scenes is you will get 3-node cluster created for you automatically. Okay, and you will also get these tokens generated. These are different tokens that we discussed. These are tokens related to security. These are not tokens that produced by partitioner, right? So, and we don't need to use them. So you just can go to, so anything here is something that you will need when you write your application. We're not going to write an application yet. We're going to use built-in client to work with this database. So at this point, you can see workshops database. Oh, it's already active. That's really cool. And in the next exercise or lab, we will go to SQL console to work with this database. Okay, and with this, Alex.
Yes. Thank you so much. I think I switch us to my screen. Thank you, and good. Okay, before we proceed, I want to answer two questions. There are two great questions in the chat. One from Melroy Tellis, and thank you for asking great questions in a row. How do the Cassandra driver and nodes perform service discovery? In short idea, each node communicates with each node. Then you launch a cluster. Nodes can join this cluster, and each server understands how many nodes are in the cluster. But that's only half of the answer. The second answer is when you have a cluster, like originally consisting of one node, two nodes, like small amount of nodes in the beginning. They share those token ranges, what Artyom was talking earlier. So each server, let's say we have free node cluster, each server responsible of approximately third of the token ranges. You have next server, they are being recalculated, and next server will be responsible, and the servers will be responsible for quarter of the tokens, like for quarter, 25% of a token range, let's say. It's a little bit more complicated because of replication, but that is a general idea. Now, each server not only knows which token ranges it's responsible for, but also knows which token ranges are its neighbors and other servers in the cluster responsible for. And the same goes to a driver. Then you launch an application, you have to specify IP address of some nodes. That is important. But a traditional approach in relational databases, for example, you specify IP address of a node in the beginning, like master server, leader server, and your application will work with this and this only server. And that is for Cassandra a complete misconception, because your node, your application driver, your Cassandra driver will use this IP address in the beginning to bootstrap information, to load information about the cluster. Then driver starts, it will go to this IP address and ask what is a cluster, what are the nodes, which node is responsible for which particular token range. Then you execute a query. Driver calculates the partition token from the partition key you gave, and then makes a query to a particular server, already knowing which servers are responsible for which partition, because it knows nodes and token ranges allocation, which server responsible for which partition tokens. Simple as that. And then this actually answers the second question by another person. Mahmoud Akhtar asks, is the request coordinator similar to load balancer? No, request coordinator isn't similar to load balancer, because load balancer is the client, the driver. For example, you have replication factor free. That means what there are free replicas of your partition is stored on 3 different servers. You try to retrieve a data from this partition, or maybe write something to this partition. You have to give a partition key. Then driver calculates a partition token based on the partition key you gave. It knows which 3 servers store your data. And then based on the round robin balancing policy, it may change from version to version, but the general idea, it tries to ask the least loaded server of those 3 to get your data. So client-side load balancing.
So it's built into driver.
Yep.
Yeah.
Yes, good question. Melroy, friend, you really need to get the Cassandra certification. Like, it's free, and it really helps you to get your LinkedIn profile page to look better and make more money in the end. I really like your question, man. So, if a node receives a request for a partition with a token outside the token range, it will behave like a query coordinator. So it sees what I'm not responsible for this token, but I know who is responsible, so I become a query coordinator or request coordinator and route this query to the proper servers, coordinate their efforts, and return the result as soon as I have this result. That's the answer. So no request is rejected. Okay, I have answered all the questions. Now it's my time to ask you some questions, right? Two questions in a row. Yes, two questions in a row. Actually, even three questions in a row. And question number one of those three will be: how many master nodes Cassandra cluster needs? Minimum three per data center. Follow replica divided by 3. No master nodes. I'm quite curious about the answers. Okay, 23 persons answer it. Right, no master nodes. There are no concept of a master node in Cassandra. No master nodes in Cassandra. No. Okay, very well. Let me see how it will go with the next question. How is data for a table distributed? Each server has all data, one table on one server, by partitions, by shards. Okay, yes, right, by partitions. We cannot have things like each server has all data. Uh,
Yeah.
because it will just not fit. Like we speak about hundreds terabytes, we speak about petabytes of data. There are no server to hold this data and still answer within milliseconds. Yeah, and there is a question, where should we answer those questions? Answer is on top of the screen. Go to menti.com and use the code 6291-8600, or you can just get the link in the chat. Good. And Tejas Kumar, I will answer your question after this quiz. Good. Right answer is by partitions. And then finally, last question. What is the biggest problem of replication? We are getting to the next section I will be doing. And what is the biggest problem of the replicated data? Increased disk space consumption, more networks transaction, or potential cross-node inconsistency? That is a tricky question. I made it intentionally very tricky. So I'm very curious of what your answer will be. And time is up. Yeah, nice. Nice. So very good. Very good. Now, it is a tricky question. So if you gave a kind of wrong answer, wait for a second, I will explain. Take a look. All of those answers are technically correct because those all are the problems of replicated data. Replicated data leads to increased disk space consumption. Replicated data leads to more network transactions. And definitely replicated data leads to potential cross-node inconsistency. But the question was, what is the biggest problem of replicated data? And the biggest problem is potential inconsistency. Let me explain. First two, disk space or network transactions. You know, there is a very good phrase. If you can solve a problem with money, it's not a problem, it's expenses. And that's exactly the same. Cassandra is used by companies like Apple or Netflix or Instagram. Those guys have money for disks. And disk space is cheap. What is priceless is your reputation. And reputation for engineers very often defined by the uptime of the application. So yeah, replication is not possible without some disk space consumption, and that is expenses, not a problem exactly. Okay, problem, but solvable problem, solvable by money. Same with network transactions. Modern software-defined networks, even software-defined networks, are extremely fast. Not to say fiber optics, blah, 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 also very, very fast. So it is a problem, yes, it's solvable, yes. But potential cross-node inconsistency is a real deal breaker. So let me show you what do I mean. Take a look. You have your data replicated on multiple servers. For example, price for the goods you are selling. And then there is an update. You want to update price, sell it more expensive, for example, I don't know, inflation or whatever. But for whatever reason, network outage, power outage, I don't know, server kidnapped by aliens, server stolen by aliens, this update didn't reach one of your servers. And as an outcome, two servers have new most up-to-date price, and second server does not, a third server does not. That is called cross-node inconsistency when one of the servers serves stale data. What happens, I mean, if you ask this or that server for the data, you get your answer and everyone is happy. But if you ask this one and this one only, that may lead to a real problem, because with even $1 difference over time on a big intensive cell may lead to big losses that we don't want you to have. So, to protect itself from potential cross-node inconsistency, Cassandra has multiple tools or layered defense. First one, we already discussed. First one was hinted handoffs, briefly mentioned before. Hinted handoff means when, for example, we process this data and this node is a query coordinator but not replica. Who are the replicas? Because this network, Forest, makes token 59, and those three servers are responsible for this token, then that means what we will send this data to those three replicas. Query coordinator sees what one of the servers does not return the answer, so not confirms receival of this update. What happens then? Query coordinator stores hint. Hint, it's a persistent data, basically, it's a file what keeps this information. As soon as this server recovers, as servers are communicating with each other, this server knows what this server has recovered, and it dispatches this hint to a replica, failed replica, so cross-node consistency is recovered. But this mechanism, although it's magical, it works perfectly, it has some limitations as well. For example, you don't want to keep your hints for too long. For example, if this server was out for a couple of days, whatever bad happened to it, it was not available for 2 days, then it will get a real storm of hints when it recovers, what may bring him to down again. Well, not exactly like this, I'm simplifying, but the story is hints usually stored only about 3 or 4 hours, depends on the version, and after that they will be discarded. If node was out less than 3 or 4 hours, it will be recovered automatically. If it isn't, you may want to execute repairs, or you may want to take it off the cluster and bring it again to the cluster as new. We will see other mechanisms. Also, we will discuss some other mechanisms to control consistency. So, hinted handoffs, we just discussed it. It's a Cassandra job. Cassandra is very good with it, and it's fully automated. You don't have to think about it. Then there is a repair on read. We will see soon in progress. Good. Then repairs. Repairs is administrator's job to configure, so it's not covered by today's workshop. If you are interested in operation and maintenance for Cassandra clusters, we have a free course on Cassandra operations available on academy.datastacks.com for free. It's called a DS210, DS210, and you are very welcome to take this one. And then finally, consistency levels. Consistency level is a developer job, and as this workshop is for developers, we will be focused mostly on the consistency levels today. Before
there are two questions. There are two
yeah,
questions,
there are,
and they are
yes, sure.
related.
Okay, so first question from Tejas Kumar. Partitioning key details are stored on all nodes. Means for each table, index is created on each node. Yes and no. I mean, it's not index in the normal understanding, like for indexing data for search capabilities. No. It is, we can call it an index, but the general idea is what each node knows token ranges allocation over the cluster. So each node knows what, for example, token is 40 or 42, and who it knows token ranges what for tokens from 40 to 50. Server A is responsible, so it knows which server to ask to take care of this data. It's kinda an index, but not in the normal relational database understanding of an index. Okay, I hope I answered this one.
Yeah, let me add. It's a very small data that metadata that needs to be stored about token ranges. So there is no need to store details of each partition key. When the data comes, that value of a partition key is runs through the partitioner, murmur3 partitioner that generates a token. So it's just very simple and quick operation. So whatever text you give or integer you give, you get one number, and that number will fall into one of the ranges. And that's very, very easy to find which range it's going to fall. There are not millions of those ranges, right? So
Yep.
and that also probably answers the next question that we have. How do we know something is a replica or not? It's based on the hash murmur3 partitioner converted into the token, and the token ranges assigned to the different nodes.
Question from CGR. Do you have visual slide which shows the overall write or read process through a series of steps? Answer is yes, but it's not the part of this workshop. It's a part of a deeper Apache Cassandra fundamentals course at the Data Stacks Academy.
And these read paths, write paths, they are not necessarily super simple. There are many different things involved there, like memory data structures, some indexes, something on multiple files on this. So these are internals. To be able to successfully use Cassandra, you don't really need to know that much in terms of the all of those data structures and how they interact.
Yep. And now to answer a question by Adriana, how do we know something is a replica or not? Short answer is each node is a replica for some partitions, right? Each node stores data. Each node is a replica. The real question is what will be the replica for the partition we are currently working with? We're working with partition like we work with these temperature data of Texas, for example, and partition as a partition key Texas. We know what will be the token of this partition as we give it to murmur3 partitioner hashing algorithm. It gives us some integer, and we know what each server in our cluster, for example, we have 6 servers, it's responsible for like 18% of bit less of the potential tokens. And we know what replication factor is 3. We already know this token ranges allocation over the cluster. So when we just make this quick comparison over the data, what Artyom mentioned already, and then we know which node is a replica for this data. It's better explain it in more details. It's explained it in our Cassandra fundamentals course at the Academy.
Yeah, and again, your application can connect to any node, and magic happens for you. You don't really need to you don't need to deal with tokens directly. You just deal with your data and tables, schema that you create.
Okay, so I guess then we switch to your part number 4, right?
Yes. So in this section, we're going to talk about cap theorem. And this theorem is very fundamental to not only to Cassandra, but to any distributed system. Okay, any distributed system. So it operates with these three features or three properties: availability, consistency, partition tolerance. And the theorem essentially says that in any distributed system, in any distributed data store, you can only choose two of these systems. You can only guarantee two of these properties: availability, consistency, or partition tolerance. So pick two. You cannot have all three. So let's look more closely at each one. What do they mean? So the availability, again, we're talking about distributed system, multiple nodes in a cluster. And availability means uptime, but essentially the availability means that if you send a request, your application send a request to the database, you will get a response. So database was available. It doesn't say, notice it doesn't say whether the response is consistent or not, whether it's 100% correct, or maybe you got stale data. Remember, because different replicas, it doesn't take, one replica maybe takes 3 milliseconds to get the data. Another one may take 7 milliseconds. So there is this very short period of time where there may be discrepancy, inconsistency in data. So availability simply says that there will be non-error response. You will get something, whether it's empty or there is some data, but it's not that you will not get an error that system is not available. That's what availability means. And we usually want to have availability, right? The other one, consistency, means that you always get you always read the data that was most recently written. So you're not going to get you will not get stale data. Okay, the old data. So in this case, in this example, we have 3 replicas. One of them still has 12, so it didn't finish the update for some reason. So in this case, this is stale data. So if we read from only this replica, we will actually get inconsistent data because the most recent value is 13, right? So that's what consistency, inconsistency means. So you kind of want to get that too, but remember, you cannot get all 3. You need to settle on 2. So it's not an easy choice sometimes. So the third one is partition tolerance. Because we're talking about cluster of nodes, bad things will happen in that cluster, right? So some nodes will go down and will no longer be in the available to respond to anything, to interact. Even you can have the network partitioning, like in this example, when these 2 nodes are no longer communicating to these 4 nodes. So it's like you have a brain split, so-called brain split, using proper terminology, and you have the group A and group B, and they are independent, and some applications may be interacting with these 4 nodes, and other applications may be interacting with these two nodes. And so the long story short, so these 3 properties, because we are working with distributed system and multiple node clusters, right? Things will happen. Nodes will go down, and just a single node going down, it's basically a network partitioning already. But think about those data centers, right? One in New York, due to snowstorm, is down. Right, so the whole data center cannot communicate with data center in California, right? So in distributed system, everyone always chooses partition tolerance. So this is fixed basically property. Every database wants to be partition tolerant, otherwise it's very hard to function in distributed world. So we only have one more peak, so we can use either consistency or availability, and therefore those systems are usually they're called CP systems or AP systems. Okay, so in case of Cassandra, I'm going to tell you right away the Cassandra is known as an AP system. Even so, we can tune it and make it a CP system, but that's not necessarily the best choice or the best way to use Cassandra. So Cassandra can use consistency levels to configure consistency, or it's so-called tunable consistency. It has tunable consistency. You can tune it. You can change it to a different. You can use different consistency levels for different requests. And essentially, each request, each insert, each delete, each update, each select that you will use in Cassandra has associated consistency level. They can be different for different requests, but they can also be the same. So it all depends on your needs. So you tune your consistency based on your needs. So you may write with one consistency and read with different consistency, which is pretty common. Okay, so here is an example. Consistency level used in Java application. This is how it's set for statement. And this is how it's used in CQL SH, CQL shell, where you can read what is current consistency level by executing consistency command or statement, or you can change, you can change the consistency by saying consistency and then specify a level. In this case, it's consistency level all. So what it means, what consistency level means is how many replicas will have to acknowledge that the operation or request was executed for the client to get the successful response, right? So we will talk about consistency levels based on some examples. So here is an example of we are writing with consistency level 1. Okay, and replication factor is 3. So client sends the request to write something, and that request is always transferred to all replicas, in this case 3 replicas. But we only, since consistency level is 1, we only need acknowledgement from 1 replica that request was successful. So out of 3 replicas, the first one that says I'm done, the coordinator will respond to client, the operation request was successful. It succeeded, the write succeeded. Okay, so no matter what happens with the other 2, maybe they will fail, but most likely in normal operations, all of them will succeed. But we are waiting for the fastest one to respond. If you need stronger guarantee, then you may use something like quorum, majority of the replicas. So in case of 3 replicas, the majority will be 2. And we will wait, the coordinator is going to wait for 2 replicas to confirm that they wrote the data for telling the client that operation succeeded. Okay, this is quorum consistency level. So, and you can change it for each write. Something that is maybe less important, consistency level 1, or there are others like local 1. Something more important, maybe quorum. And consistency level all will require all replicas to confirm that they read in the data. And consistency level all is a bad one. So we don't ever want to use it. Why? Because if you're gonna wait for all replicas, essentially we are going to enforce consistent write, but we are going to make our system unavailable. We are going to sacrifice availability, because if one of those replicas goes down, we will not be able to complete the write, because there are only 3 replicas. If one of them is down, then consistency level all cannot be satisfied. Quorum can be satisfied, right? Because 2 out of 3 is still available. 1 can be satisfied, 1 out of 3 is still available, but just one failure and your system is not available. So that's not a good situation. Essentially, this is example of when we sacrificing availability and using Cassandra as CP system, which is not recommended. Don't use consistency level. Okay. But then you may ask, well, I don't want to ever read stale data. I want to have consistency. It doesn't matter. I want availability. I want some consistency. And we can do that as well. We can still sacrifice some availability, but make sure we have better consistency. And that better consistency essentially is called the immediate consistency or strong consistency. So let's see how it works. Essentially, the formula for, so you need to, if you want to make sure that you write something and then you immediately read and you read most recent data, no stale data, then you need to make sure that your consistency level for writes plus consistency level for reads is greater than replication factor. So in this example, this is the case. So replication factor is 3 and consistency level quorum majority of 3 is 2. So we're reading with 2, we're writing with 2, and we're reading with quorum, which is 2 as well. So 2 plus 2 is 4, is greater than 3, right? So we are gonna get immediate or strong consistency in this case. So this client writes the data. It writes into 3 replicas and waits for 2 confirmations. So these 2 confirmed. This one may be slow. Maybe it's gonna take 10 milliseconds, and these 2 did it in 3 milliseconds. Immediately, we have a client that is reading the same data and doing it fast, so less than 10 milliseconds passed. And it's in case of reading, because we're reading with quorum, we don't have to contact all the replicas. We're going to contact only 2. So let's say we contacting these 2. This one actually has the most up-to-date data, and this one still has stale data because the write didn't complete. So what happens? We get both of them on the coordinator node, the request coordinator node, and based on the timestamp, every piece of data in Cassandra has a timestamp that is there automatically. So based on the timestamp, the most recent data is going to be identified and returned to the client. And besides that, even there is a chance that the coordinator will send the most recent data to this node to make sure it's gonna have it next time it talks to it. So this is essentially allows you to always be consistent and allows you for availability. If one node fails, with replication factor of 3, your system still functions. You will basically not notice. Your application will continue to serve the requests. Now, there are many consistency levels. This is not the complete list. So the edge cases, any and all, is something you should not use. So any is only used for writes, and it's when no replicas available. So the coordinator node is going to store the data as a hint. So this is something that you don't want to use, and all you don't want to use.
Well, it very depends on the use case. I mean, like in general case, yes, you don't want to use any, you don't want to use all. But don't forget what consistency level is configurable per query, and it also may depend on the what kind of a data you are storing. There are plenty of scenarios when any will be fine for you, but it's not as a general rule, not as a rule of thumb. Only when you work with the data you can afford to lose, but you have really intensive write performance, for example, for logs, for the data which is being outdated within few seconds. So there are some scenarios when any is a good thing. I don't want like to say never use any. But definitely, as a rule of thumb, we don't use it, and you have to be very careful. It may potentially lead to the inconsistency. The story is there are some scenarios you can afford inconsistency.
Well, yeah, I've never heard anyone using any in production, and the cluster will be in a very bad condition if you have to use any, essentially, because all replicas are down, and the data is not going to be stored properly. It's going to be stored on the other node, but it's not going to be in proper data structures and all of that. Anyway, the most important ones will be one local one. Some 2, 3 is okay, but most of the most important ones will be one local one, quorum, local quorum, each quorum. So what one means, if you have these three data centers, but one cluster, they all in one cluster. So one means that any replica in this whole cluster can respond, can acknowledge. Okay, your write or read. Local one means that if your client connects to this left data center, leftmost, then the replica in this data center must respond. And that brings us the question we had earlier: will multiple data centers affect latency? So if you're using local one, it will not, because you're only going to get response from replica in the same data center that you connected to. So you don't need to, if you connected to one in New York, you don't need to get the response from Tokyo data center. Okay. There are two nodes or two replicas or three replicas in the whole cluster. So that's not super useful, actually. Quorum means majority of the replicas in the whole cluster. So we have 3 replicas in each one. So we have 9 replicas in the cluster. We need to get response from 5 of them. Okay. So again, if you're using multi data center environment, then you probably like to use local quorum, because it's gonna be quorum of the replicas in local data center. If I'm connected to leftmost, and there are 3 replicas, local quorum means I want to get response from 2. I don't need again to go to Tokyo or go to New Zealand to get my answers, right? Because I'm in California, I want the data that is stored here locally. It's going to be more efficient. And each quorum is a quorum in each data center. So if we have replication factor in all 3 of them, we need to get a response from 2, 2, and 2. So totally 6 nodes. 6 nodes need to respond.
Geographically distributed nodes, it's not going to be fast.
It's not gonna be fast. Yes, it's the most expensive out of all of this, except of all, of course. So
Yeah.
all is gonna require 9 replicas to respond. So you get the idea. Each request, write or read, will have to use some consistency level, and you may easily write. So when you, for example, if you write with local one, the data you'll get confirmation, the application will get confirmation from only one, right? The one replica. It doesn't mean that the others are not writing. They are writing at that time, and one of them becomes the coordinator for replication with another data center. And these two coordinators communicate and write into these replicas. All of this happens for you, but you are not waiting for this process to complete. You just waiting one local node acknowledgement. So that's going to be very fast. But then you may decide reads are more important. I'm going to read with local quorum or something like that. Okay, and with this said, we can proceed to the second lab. Okay. So again, I'm going back to GitHub repo, and we are going to create tables. Those tables will look very much like SQL tables, very much like SQL tables, right? And even so, the SQL, Cassandra query language. So let's take a look what we need to do. We can describe key spaces, this command. So we will basically see what key spaces we will have in our system. I will do that for you. You will take a look at that. We will then choose to use sensor data as a key space. And then we will create 3 tables. One is networks table, which is a table with name. So it stores sensor information about sensor networks, name, description, and region. So name will be partition key. And we can later check that we did create this table. And then we create two more tables. One is sensors by network, and the other one is temperatures by network bed. So this is going to be a bed table. And the reason it's bad is because partitions, that's something that Alex will talk in the next section, but essentially the partition key is sensor, and all the temperatures measured by that sensor will be stored in that partition. But you can think that if that sensor is working for many years, it's going to collect data for many years and collects data regularly, every second, every 5 seconds, every minute, and so on, then that partition will grow. It's going to have many, many rows over time. And we don't want that to happen. We want to put a limit on the size. And therefore, later we will drop this table, and create table temperatures by sensors, where we will add date as part of the partition key. In this case, we collecting the measurements of each sensor on a specific date. Okay, on a specific date. So this allows us to limit the size. Whatever data is collected on that date, the partition stops, right? Then the next partition is created tomorrow, and so on and so on. So only 3 tables at the end. Let's see what we can do. Let me copy the first table. Okay. Okay. Okay, and I was logged out. I will log in again, go to databases. Okay, I have my workshop database. I will click on it. You have the same workshops database. And we will use built-in client to interact. Okay, so essentially it's the client, someone written for us in Python, and we are going to use it to interact with our database. So first, describe key spaces. Okay, so the key space that we're interested in is this sensor data. Other key spaces here are key spaces that are related to the database, metadata, functioning, and so on and so on. So these are basically internal key spaces that you should not work with. The one we created is sensor data, and we are going to use it. So we're going to select it as a default key space. All our statements will be executed within this key space. Okay, now let me copy again. Okay. So I'm going to create this table. Done. Describe tables. Okay, I only have one. Describe this table networks. Oh, you can see the same code, create table, but there are a bunch of other properties that you can actually change for the table, and I'm going to talk about them today. So the other 2 tables. Okay, sensors by network and temperatures by sensor bed. Okay. And the last command that we need here is to drop that. I explained why that table schema was not great. The selection of primary key was not great, so we added date. So we will drop that table and create a new one. Okay, now let's describe our tables. And we have 3 tables, right? And now in the next exercise, we will be able to populate those tables. Okay, we will be able to insert, delete, update. So if you're familiar with relational databases, with SQL, then you probably feel comfortable using CQL, Cassandra Query Language, create table, insert, delete, update, select, all similar statements, But there are some differences we've seen already, like the partition key and this clustering order by is something new. What it does is basically specifies how the data will be sorted within each partition. Within each partition, the data is sorted based on clustering key, in this case timestamp, and we're saying let's sort them in descending order. So the most recent data is going to be first, and this is kind of optimization that allows you to efficiently retrieve the data and do some specific queries that clustering order helps in that case. But that's out of scope for today. Alex, back to you.
Yep. Good. So questions are answered in chat. And let me switch to my screen. Yes, good. So with that said and done, let me ask you a couple of questions to be basically the very last questions of okay, almost the last question. CEP theorem says what on failure? C, A, and P are guaranteed. If C fails, so do A and P. Only CA or CP can be guaranteed. Time is almost over. I'm so happy you are still in this quiz and answering yes. CA or CP can be guaranteed. You cannot. That would be great to have CA and P on failure magically somehow, but there are no unicorns. I'm sorry. Although that would be great. Yep. And if C fails, A and B still can be feasible. Good. Then second question. Recommended consistency level for the immediate consistency. Read write 1-1, read write 1-all, read write quorum. Yeah, read write quorum is recommended level for immediate consistency. Those 4 persons who answer it 1-all, technically you are right. 1-all also let you reach immediate consistency. But it's not recommended way, because this way you are in a trap of all consistency level, which require all nodes to be available, and the slowest one. Good. So we are getting to the very end, final part, and let me lead you through that. So data structure in Cassandra starts with a cell. A cell is an intersection of a row and column that stores data. Then row is a single structured data item in a table that must be familiar to you already. Then partition is a group of rows having the same partition token. It's a base unit of access in Cassandra. It's important what all rows of the same partition will be stored together on the same server, close to each other. It's important for the smooth retrieval of this data. Then finally, table is a group of columns and rows storing the partition. In Cassandra, data is organized as distributed tables. So tables are present, but parts of them are spread over multiple nodes. and then responsible for that is a partition key. Then you create a table, you must define primary key, and primary key consists of two parts. First part is a partition key, first argument in a primary key definition. It may consist of one or multiple columns, but must present and must have at least one column, otherwise we cannot calculate the token. Very different ways, but the general idea is all the fields of the partition key, in this case, for example, only sensor, we will have as many partitions, as many sensors we have. Is it good or bad? Well, it depends on your situation. It might be good or bad depending on how many sensors do you have. Well, you can have many partitions. It's totally fine. But maybe you want to improve something on that. In this case, you see, sensor and timestamp. Partition token will be generated based on sensor ID and timestamp of a temperature record. That means we will have as many partitions, as many records we have per sensor. And that might be good on the write time, but it might be bad on the read time. Very important thing to understand when we're thinking about creating partitions. We speak more about that next workshop, but briefly I want to introduce it. When thinking of partitions, we need to remember two operations, write and read. What is important? During all the operations, when we write data, when we retrieve data, we need to know all the parts of the partition key. Can we write data with this partition key? For example, temperature sensor reports its temperature to be, I don't know, 30 degrees Celsius. Can we write this data? Yes, we can. We know sensor ID, we know timestamp when this recording was done. When we can just go throw it to the database and we will be happy. New partition will be created. This partition will have only one record, and all of this is totally fine and good. But you should not forget about the second operation, which is read. And in this case, we might run into trouble because to retrieve this data, again, we need to know all the parts of a partition key. And then take a look. If we are going to retrieve data about a sensor, I think we may have its ID. Okay. But also to retrieve data safely in the right way, we will need to know all the timestamps when these recordings were done. And that sounds already not so easy. So this partition key might be optimal for write, but not so optimal for read. So we could think of something better in the future. Then, second part of a primary key are the clustering columns. What is a clustering column? It's a special column, part of your table definition. In this case, for example, timestamp. What has two purposes? It's used to ensure uniqueness, and its second duty is to ensure sorting order. First, let's think about uniqueness. Why do we use clustering column? Imagine primary key like that. We don't have clustering columns at all. We have only partition key, and partition key is sensor. So sensor ID. With this design, we will have one recording per sensor because primary key will be always matching. Cassandra follows the logic of upsert, where update or insert are exactly the same operations. So with that, if you use primary key like that, every next temperature recording will overwrite the previous recording. Is it good or bad? It depends on what do you want to have. If you are fine having only the last recording, then maybe it's totally fine as designed. But if you are going to see like how temperature changes over time, that's obviously not going to be the good idea. So short answer is not unique. Then, for example, second duty of it is to have sorted defaults. This idea is much better. Sensor as a partition key, timestamp as a clustering column. This way, because they both build together the same primary key, each new recording will be unique and available for sensor, for timestamp. And that is the first thing. So data is unique, and next timestamp recording next temperature recording will not overwrite the previous one. And in this case, we will be able to sort by time, and that is already pretty good for us, because, for example, we want to sort our temperatures by time to see how it changes over time. In this case, it's a pretty good example how timestamp is used for both uniqueness of the record and for sorting. That is a pretty good example. Let's move on. Then primary key is partition key and clustering column all together. You already seen how they're working. Partitioning, so partition key is used to define partitions. Clustering column is used for uniqueness and for sorting order. And this with clustering order by is used to explain in which sorting order we need to have it ascending or descending. So those are typical examples of a primary key, for example, for this kind of data. Can we mention clustering order out of a primary key columns? So I'm not sure if I can get the question. Can
Maybe
we
use
mention clustering?
non-primary key columns? Can we use non-primary key columns to
for
specify?
sorting?
Yeah. Yes.
Maybe. So the story is in Cassandra, clustering or okay. So the story is we have three kinds of columns. Partition columns, so sensor and date in this example, clustering columns, timestamp in this example, and data columns, value in this case. Why value is a data column? Because it's not mentioned in primary key, nowhere. And in Cassandra, partition key, clustering columns work as primary indexes. So you can use them for search and clustering columns for filtering, for sorting. Data columns cannot be used for search, for filtering, for sorting, and so on. They are just to store data. There are tools to enable it, like secondary indexes, but secondary indexes as Cassandra is a pretty complex topic. They had their own issues. They partition based, and there are like plenty of issues with that. So short answer is for sorting.
Only clustering key columns.
Yeah, for sorting, for only inequality operations, only clustering columns. I told you in the very beginning, Cassandra is a real firepower on the database market. Extremely fast, extremely powerful, scalable, and high availability and everything. But there are plenty of limitations too. There is a price to pay, and inability to search by data columns or inability to use inequalities on partition keys is part of this price. We will discuss it more, I believe, in the next workshop. Good. Now, very important thing. Now, please focus. They are getting to the end, and this part is important. Partition keys define data distribution over cluster. All right? A different partition key, and your data goes to another server. Clustering columns define how data is physically stored, how it's physically written on disk. So, there is a very important thing you need to understand because of that. Once created, data model cannot be changed. You will need, if you find what your data model is not right, if you have something, maybe it was right before, but now it's changed, now your application has new business requirements, you may need to create new tables and migrate your data. And there is no things like alter table, change primary key. It's not possible. For a simple reason, schema is immutable, because changing any kind of a partition key will lead to changing partition tokens, will lead to moving all data, all the cluster, and basically that can take weeks and your cluster will be busy moving data, not answering customers. Same with clustering columns. Change of a clustering column will lead to the need to rewrite all data on your cluster, which again will take weeks of cluster being busy or rewriting your data. So it's again not possible. You can change only data columns. You cannot change anything what is or was a part is a part of a primary key. Nothing. Schema is immutable. Good. And that last few slides. Partitioning, as you can understand, is the key to success. If you do your partitioning right, your application will work very fast and it will be very scalable. Do your partitioning wrong and you will have a lot of fun later. I mean fun in the very bad meaning of this word. So no fun at all. Very three simple rules of a good partition. First, store together what you retrieve together. That means think about how you are going to load the data, select, read these data. The data makes sense to group together what you are going to retrieve together. We have to try to group our data away. So everything will be retrieved from one single server, so it will belong to one single partition because data is isolated on the partition level. That's it. Second rule, avoid big partitions. Don't forget, we introduce partitions to avoid having too much data per server. And introducing two big partitions, you get to exactly the same problem. You just get too much data on the server. Your server will need to spend a lot of time trying to retrieve your data. It will be unmaintainable and very many other problems. For example, we do not recommend you to have more than 100,000 rows in a partition or more than 100 megabytes of data in a partition. Those are recommendations, but the hard limit, you cannot have more than 2 billion cells per partition. But my advice is not to try to get any close to this number because it's going to be a very, 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 very bad idea. For example, here we can say what writing comments per video on YouTube, for example, those are small entities, so sometimes there can be more than 100,000 rows in a partition, but at least they are small. There is a text, comment ID, author name, timestamp, and text, and usually comments on YouTube is pretty small. So in this case, partition per video for most of the cases will be of a reasonable size. But if you group your data, customer data, your users based on the country, there are countries like Vatican or San Marino, there's like a couple of thousands of people, and there are countries like China, India, and with hundreds, millions, maybe billions of people. And this case, you first introduce big partitions, which is bad. And second, you introduce uneven partitions, which is even worse. You see, Cassandra scalability works best when your partitions of a similar size or they are more or less even. Then spreading things like that based on a country is basically obviously a wrong idea. And then another point, what is very often forgotten designing partitioning for these tables, people forget what size may change over time. For example, if you write this temperature sensor and you do it like that, sensor ID times temp. The example we are speaking all the day today with temperature recordings. If these sensors report their state frequently, like every few seconds, if we speak not about like nature research, but we speak about Internet of Things, temperature of an engine, temperature of oil in the engine, then this temperature can be recorded every few seconds. And then over time, if at the beginning this model will work, partitioning based on a sensor ID, then over months, the partitions will start to become too big. And obviously that's getting dangerous. Our partitions are too big. One of the solutions possible in this scenario would be introduce some sort of a bucketing. where we have these, where we add one more field to a partition key to be the month and the year of when this recording was done. So that is the January of 2023, and then this value will be 2023-01. Then what happens? Then this month is over and February starts. So it will be 2023-02. That means what, for the very same sensor, this value will be different, which brings us a new token, and therefore a new partition is created. Automatically, you don't have to think about it, but then just you have new partition and it all works on a new node, and it's scalable. Therefore, when you will add more servers, partition will move to different places, to different servers. Very well. Sometimes people ask me, why not to put a timestamp in the partition key? Or not build it based on month, but build it based on week, maybe day, maybe hour, things like that. Don't forget two access patterns, write and read. Can I write sensor ID month year? Yes, I can. Can I write sensor ID timestamp? Yes, I can. But then second access pattern, read. Can I read sensor ID in month year? If customer asks me to show data values of a sensor for last 3 months, it will be January, December, November. So plus the same sensor ID. I will hit 3 different partitions. Not a big deal. It's okay. But if I have my partitioning based on a week or a day, for 3 last months, I will need to hit like 90 plus partitions. That is obviously a bad idea. And then finally, avoid hot partitions. Imagine for our temperature recordings, we do partitioning like that, date and sensor with partitioning based on the date, current date. Then take a look, I have a cluster of 10 servers and replication factor 3. So today, all sensors write to those 3 servers. Servers are very busy because I have a lot of sensors, maybe billion of them, maybe multiple billions, a lot of writes. And servers are basically dying because there is too much pressure on them. They cannot process all the queries. And that is a bad. And then I think, okay, I work for a big company. We have a lot of money. We will buy 10 more servers. So my cluster will be 20 servers. And we do. Will that work? No, that will not, because despite now I have 20 servers, very same partitions allocated on the very same server, or maybe new servers, but it's still the same. 3 servers are overloaded because of replication factor 3. Partition is hot, it's being accessed all the time, while all the other partitions are not being accessed at all, or only for reads. That means we need to think about the size of a partition, about how often those partitions are being accessed in the terms of writes and reads. Avoid hot partitions, partitions being accessed all the time, while others are idling. So this approach is much better because when I need to scale, I add more servers, and those workload is being distributed across multiple servers. Each server has less amount of queries per second. Basically, last question. Okay. All right. All right. 2 last questions. Question number 8. Select without partition key. Syntax error. Okay to get all data. Very bad, illegal, and punishable by law. Now, as an officer of NoSQL police, I have to say what answer number 4 is right. I will get to you and arrest you if you are trying to do select without partition key in Cassandra. Yeah, so no, it's not a syntax error. You can do select without partition key. You will get an error by default, but it's not a syntax error. And you can make select without partition key working with allow filtering statement, but it's a bad idea. Second, it's okay to get all data. No, it's not okay to get all data. It is indeed very bad. In some scenarios, it might work if you use allow filtering. And last one, whatever you are, whoever you are who said illegal and punishable by law, thank you so much. Like I'm all with you. Good. And the last question for today, question number 9, is what is the most important rule of partitioned data? Try to have as many partitions as possible. Keep partition size under control. Keep together what you retrieve together. And last one, make partitions bigger. Okay, don't make me angry. Don't pick the four. Okay, thank you. Yes. So now, keep together what you retrieve together is a question of convenience. It's important rule. It may be very helpful on the read time. That is a very good rule. But when your cluster is operational, you can remodel it. You can create new tables. You can migrate your data. But when your partitions went crazy size and your nodes just irresponsive, and you cannot do anything, that is a really bad situation. So the most important rule is keep partition size under control. Don't make too big partitions, or avoid big partitions, avoid hot partitions. That brings us to the last slide of the quiz. Who made the best work answering questions? And like each question worth 9,000 points. So many thanks to Tejas Kumar with 7 right answers. Then James, Melroy, Natalia, Sudharsan, Bell, Ivo, Ranjit, Twito, and JD. Thank you so much for making it. And Tejas Kumar, that was incredible job. Perfect. With that, thank you for participating. You are the best. I think, Artyom, what do you think if we keep last step of the homework to be the homework? That is the first step of the homework. It's assigned to be homework.
Yeah, I don't mind because it's very easy and the instructions are quite comprehensive. So
there is a
inserts, updates, deletes, and selects. Yeah.
There is a good question from James Wong. Do we need to constantly archive all data to keep database clean, I guess? So James, first of all, Cassandra has native tool to wipe out old data if you don't need it. So for example, if you define what you're not going to need temperature recordings for longer than for 1 year or more, you can creating or writing data, you can specify TTL, time to leave. So this data will be automatically deleted then this time is expired, which is pretty cool. But in some scenarios, you do need to keep data for longer times, and you do want to keep it still under control. In some scenarios, you indeed may want to unload some old data, put it on AWS S3 or some another kind of a cold storage if you're not going to access it often, and you will be fine with that. But the story is you don't necessarily have to. Like if you're going to really read this data from time to time and access this data from time to time, then it may be perfectly fine to just keep it there as long as your partitions are designed well and you need to store more data. Don't forget, you want to store more data, add more nodes, and it will be scaled automatically. That is like very typical thing. Good question from Andre. There is a tool for archiving. Yes, sure. Tool recently published, well, how recently, some years ago, published by DataStax, called it DS Bulk. DS Bulk. For some scenarios, you might want to use Apache Spark to get some more advanced access to data, and things like that. Thank you so much Tejas Kumar, for your kind words. Yeah, Billy, we do have all the recordings for this and our workshops, same link. So coming in. After some data is deleted, how is it reordered on the physical level? Oh, great question. Ivo Rambaldi. A very good question. That's completely out of scope for today's workshop, but in short, there is a process similar to vacuuming in relational databases, call it compaction. Compaction comes in order regularly to clean up deleted data, to clean up updated information, what is not in the previous version. The story is like you are here with us till the very end, even overtime. So I want to open some secrets. Story is Cassandra is extremely fast for writes, but it requires some very advanced optimizations on write path. Then you write data, some very advanced optimizations. One of them is very interesting. Take a look. In Cassandra, insert, update, and delete are exactly the same operation internally. Now, you might be surprised. Insert or update are the same operation. Okay, that's understandable. But how come delete is the same operation? The story is, when we write data, what is the slowest operation in software development, in software operations in general? It's changing data on disk, any kind of a disk operations. But especially changing something, so you need to find, you need to update, you need to move, a lot of things. It's slow. Cassandra designed it to be very fast. So every time you do anything, any mutation with your data, it's always append only operation, what goes on the bottom, let's say, of the things. And over time, you get information being stored too much time. First value, update for the same value, update for the same value, and then finally it's deleted. You don't sell this thing anymore, and you don't want to store its data, and you want to retrieve some disk space. Then as a result, it will be original value, new value, next value, and dumpstone. Dumpstone is a special marker what this data has been deleted. So you have basically 4 entries for the same data, although technically it's kind of deleted. Compaction is the process what takes these immutable files. Those files are called SS tables, sorted string table files, and then it makes compaction on them, removing all the old values, removing all the dumpstones, deleting all data, and writing a new file on disk, which now will be it alone, and the old files will be deleted. This process happens in background. You don't encounter it when you routinely write or read data. It happens in background. And that is the story how insert, update, and delete are the same operation internally. And that is just one of the many cool optimizations inside the Cassandra. I hope I answered this question, Ivo. What happened if there is a inconsistent data read? Is there a way to acknowledge or recover? So when we read data, so it depends on your consistency level. If you read data and then you require consistency level quorum or all, or any consistency level high enough, and then node sees, query coordinator sees what someone is outdated, then query coordinator will initiate repair and consistency will be recovered. It happens in background, it's automated. But if you read with consistency level low, if you read with consistency level 1, for example, and your node stores inconsistent information, then you will get inconsistent information, and that might happen if you use too aggressive consistency levels like 1, for example. So you have to be careful with that. Does this method not preserve the meant order? This method, compaction, indeed preserves the meant order. It preserves the order defined by clustering columns. Does Cassandra support updating multiple rows in a single query? Short answer is it's complicated because you see, if rows are in different partitions, they will belong to different servers, and that is going to be a totally different story. So you can actually, Artyom, if I'm trying to make an update, I have to specify partition key.
Yeah, well.
So yes, answer is yes. Yes.
Okay. So it's not going to be in one update statement. So you will have to issue multiple update statements, but the internally, if those update or insert statements belong to the same partition, internal optimization will do that update as one single update. Even so, you issued multiple update statements. And there is a corner case, static columns. If you update a static column in the partition, all rows will be affected.
Yeah. So short answer is yes. Good. So looks like there are no more questions. Then I proceed to the very last slide. What's next? Homework is to finish the hands-on lab and submit your homework for this workshop using the link which is mentioned in the GitHub repo. You will find it in the homework part. Links you might want to have. Our Discord server to talk to us and to have us answering your questions in between of workshops. Discord, I'm showing it, HTTPS. Yep. Academy. So if you decide what, yes, you want to work with Cassandra, it's powerful, it probably gonna make me some money and very interesting technology to work with, then you can proceed at academy.datastacks.com to get your developer path or administrator path and get certified for free. Link for the workshops is on the screen. See you next week. One more time, in case you missed that, I posted already links to our LinkedIn. So if you aren't in, then please jump in and add us on LinkedIn. Always pleasure to answer your questions. With that was Artyom Chabatko and Alex Voloshev. Thank you so much for being with us. And see you next week then. It will be Artyom and who will be with you tomorrow or next week?
Aaron.
Aaron Klotz,
who is in the chat today, yes.
Yeah, and a great expert, book author, like one of the best experts in the Cassandra field. So you are like him. Then, good luck. So don't forget to submit your homework and see you next week.
See you next week. Thank you.